Let's step back to the year 1970. We are outside the Ambe Cafe, a typical diner in an era where commerce was handled with physical coins for every tiny fraction of a rupee. Even then, physical reality rarely fit into perfectly clean whole numbers. Whether you were measuring ingredients or settling a bill, you almost always ended up with fragments that fell between the units of a whole rupee or a whole centimeter. On this antique bill, the total comes to exactly 1.77 rupees. That's 3 doses for 1.50, 2 teas for 0.12, and a cake for 0.15. That 0.77 represents 77 subunits. Without the decimal point, these leftovers would be difficult to record or add to other totals. We need a system that treats these fragments with the same precision as whole numbers. These are the physical versions of those fragments. Paise. In 1970, these coins were common currency, with exactly 100 paise making a single rupee. Converting these into a standard format is a matter of division. Because a rupee has 100 parts, 75 paise is written as 75 over 100, or 0.75 rupees. While most of these physical coins were removed from circulation by 2011, this division by 100 remains the standard for how bank statements and digital bills are calculated. This same system applies when we measure physical objects. As we move into a microscopic world, standard centimeters quickly become too large to be useful. Look at the metric scale. Since 1 centimeter contains 10 millimeters, a single millimeter is exactly 1/10 of a centimeter. In decimal form, we write this as 0.1 centimeters. We use this precision to record the size of the world's smallest creatures. This is the Carabera bruni ant, which measures only 0.8 to 1 millimeter in length. Next to it is the Acmella nana, a land snail with a shell diameter of 0.7 millimeters. Using decimal notation allows scientists to categorize these microscopic dimensions without losing the relationship to the larger centimeter scale. The system scales further when we measure mass. Here, the standard is the kilogram, which is comprised of exactly 1,000 grams. To express a single gram as a fraction of a kilogram, we divide by 1,000, resulting in the decimal 0.001 kilograms. This allows us to compare vastly different scales. We can measure the wolfie octopus, which weighs less than 1 gram, using the same system we use for large-scale agriculture. If you take 5 piles of rice, 1 gram, 10 grams, 100 grams, 1 kilogram, and 10 kilograms, and put them on a single scale, they combine to form the sequence 11.111 kilograms. Decimal notation provides a shared framework. It allows us to track massive shipments of grain while still accounting for the weight of the tiniest marine life. Reliable conversion depends on the unit barrier rule, keeping your place value columns perfectly aligned. To convert smaller units to larger ones, you divide by tens, hundreds, or thousands. 1 millimeter becomes 0.1 centimeters, and 1 gram becomes 0.001 kilograms. We can apply this to a real-world scenario from the Indian Railways. Passengers booking e-tickets are offered travel insurance for a very small fee. The insurance costs 45 paise per passenger. If 1 lakh people opt for this insurance in a single day, what is the total fee paid in rupees? Use what you've learned about decimals to convert those paise into a rupee total, and post your answer in the comments. By using decimal notation, you can bridge the gap between large-scale numbers and these small subunits.